Hi guys, welcome back. So today what we're going to be looking at is calculating empirical and molecular formulas. So when I was back at school and when we were learning chemistry, we didn't really learn about this sort of stuff. And I think that really was to my detriment in a way, because when I went to university, right, like when you're going and you're discovering things in chemistry, quite often what you're looking for is you're looking for a new compound or a new molecule that can perform a particular role. So what you do is you go out, you collect a whole bunch of random stuff, or maybe you synthesize a whole bunch of random stuff depending on what type of chemist you are, and then you test the particular properties of these random compounds that you've come up with. Now, a lot of the times, especially if you've gotten something from nature, you don't actually know what the chemical composition of those compounds is, and so you'll run different tests on them. So for example, like a mass spec test, and then you'll get certain information back from that. And then using that information, then you have to sort of piece the puzzle together so that you can work out what the compound actually is. So this is actually really useful for you guys, especially if you're going to go on and do chemistry at university. So our learning goal for today is that we are understanding that the empirical formula expresses the simplest whole number ratio of elements in a compound. We're going to do this by calculating the percentage composition, and we're going to determine empirical and molecular formulas of compounds. So we've got 4 new terms to add to our vocabulary. We've got relative atomic mass, percentage composition, empirical formula, and molecular formula. All right, so let's go through and let's talk about, let's talk about percentage composition to start off with. So percentage composition just tells us what mass a particular compound takes up, a particular atom takes up within a compound. So for example, if I had a compound that had the atoms A and B, where A and B are different atoms, the percentage composition of A can be found by using this formula here. So the percentage composition of A is equal to the mass of A divided by the total mass times by 100 to make it a percentage. So for example, I've got an example here with CH3COOH, and I want to work out the percentage composition of each element within that. So I've got 2 carbons in this atom, and each carbon atom has a molar mass of 12 grams per mole. So that means I'll have 24 grams in total of 1 mole of this substance of carbon. If I have a look at hydrogen's about 1 gram per mole, and I've got 4 of them, so that means I'm going to have about 4 grams in 1 mole of this compound. Lastly, I need to determine what oxygen is going to be, and I know that the molar mass of oxygen is 16. I've got 2 oxygens here, so if I have 1 mole of this substance, that means I'm going to have 32 grams of oxygen. I also went ahead and I calculated the molar mass for this compound, and I just did that by going and adding up all of the carbon atoms. So 2 lots of 12 makes 24, plus 4, plus 2 lots of 16, and that's how I got my value of 60 grams per mole. By the way, I'm just assuming I've only got 1 mole of this substance. All right, so let's chuck this now into my formula. So what I want to do is I want to work out the percentage composition of each of these different elements. So the percentage of carbon is going to be equal to the mass of carbon divided by the mass of the total compound, which is CH3COOH. The next thing times 100. Next thing I'm going to do is I'm going to substitute in those values. So like we said before, I've got 2 carbons in here. So if I have 1 mole of this substance, that's going to weigh 24 grams. And the total mass of this compound, assuming I have 1 mole, is going to be 60 grams. And then times that by 100 to make it a percentage. So just going to quickly chuck that into my calculator. So 24 divided by 60 times by 100 is going to be a nice round 40%. So the percentage composition of carbon is going to be 40%. Let's go ahead and let's do the same thing now for the hydrogen and the oxygen. So again, I'm just assuming that I've got 1 mole of this substance. So 1 mole of this substance would contain 4 grams of hydrogen. So let's substitute this into our formula. I'm not going to write the formula just for the sake of brevity. So 4 grams out of the total 60 grams is going to be hydrogen times by 100 to make it a percentage. Let's chuck that in our calculators really quickly. And that's going to be 6.66%. So in other words, 6 2/3 of a percent. All right, well, we can work out oxygen now. We could add this up and we know that we've got 46 and 2/3 of the mass accounted for. So we could do 100% minus 46 and 2/3. I still want to show you using this formula though. So let's go ahead and do this last one. So percentage composition of oxygen. So 32 grams out of the total 60 grams is going to be oxygen times by 100 to make it a percentage. So again, I'm just going to chuck that into my calculator, and that's going to give me 53.333% or 53 and 1/3%. I think we should write this as a decimal actually. I'm in such a habit of writing fractions because I do teach maths, as you guys know, because I did have most of you for maths last year. Oh, we're not doing a recurring decimal because we rounded. Okay, so those are my relative percentage compositions of each of the elements in CH3COOH. All right, I want you guys to have a go now at this question 3 on page 177. So I want you to determine the percentage composition of each element in glucose. So what I'm going to do, I'm going to work out the answers off camera, and then I'm going to pop up the solution. So if you want to pause the video now so that you can have a go, and then I will give you the answers after the break. All right. So I'm going to pop the answers up now, and I didn't realize this before I did the video, but we actually have the exact same values as what we did for our previous question. And I think the reason that we have the exact same answers is because the ratio of elements is actually the same in both of these compounds. I didn't realize. So this would be C2H4O2. So in other words, it's a 1:2:1 ratio of carbon to hydrogen to oxygen. And this is actually the exact same ratio. So the percentage composition actually works out to be the same thing. Whoopsie. Oh well. Okay, so let's go through and let's talk about empirical formulas. Ooh, my computer keeps freezing. Apologies. So an empirical formula is just like a simplified ratio. So it's not actually telling you all the numbers of atoms within a particular compound. Okay, so it's the simplified formula. So for example, we've got a compound, and that compound contains 40% carbon, 6.7% hydrogen, and 53.3% oxygen by mass. And it wants you to determine the empirical formula of the compound. So first things first, we're going to assume that there's 100 grams of this substance. It's going to make my calculations a whole bunch easier, because if I have 40% carbon and 40% of 100 grams, that means that I've got 40 grams of carbon. So that makes that one nice and easy for me. This also means I would have 6.7 grams of hydrogen, and then I would also have 53.3 grams of oxygen by mass. All right, so this is where it gets a little bit funny, because what we actually need to do now is we actually need to work out the number of moles of each of these substances. So big hint for you guys, whenever you're given the mass of something, always go back to the number of moles. Always do that conversion using that formula. So I'll just pop that over here. So molar mass is equal to the mass per mole. All right, so let's go ahead and do this for carbon now. So we know that the molar mass for carbon is 12 grams per mole. Okay, and so if we substitute that into our formula, 12 is going to be equal to 40 divided by n. I'm going to rearrange this formula to n is 40 divided by 12, and I'm just going to quickly chuck that into my calculator. So that's going to be equal to 3 1/3, so let's just do 3.3. Same thing now with hydrogen. So we always want to go back and we always want to convert into moles. So the molar mass of hydrogen is going to be about 1. Technically, it's like 1.01 or something grams per mole. So I'm just going to do the same rearrangement. So the number of moles is going to be equal to 6.7 divided by 1.01. And that's going to give me 6.7 divided by 1.01, 6.63. So 6.63 moles. Sorry, I should put the units there, shouldn't I? Same thing, I should put the units. All right, lastly, we've got oxygen. Now, the molar mass of oxygen is 16 grams per mole, so we're just going to substitute that into our formula. So 53.3 divided by 16, and let's just chuck that in our calculator, is going to be 3.3312, so let's just round that to 3.3. So if I write this as a ratio, I'm just going to take the first decimal place I think is going to be easiest. the ratio of carbon to hydrogen to oxygen, and remember we're always going to compare the moles, we're not going to compare the mass because the molar mass is going to be different for each of these. So we're going to have the ratio 3.3 to 6.6 to 3.3. So now all I'm going to do is I'm just going to divide this ratio by the smallest number, which is going to be 3.3, and I'm going to be left with the ratio 1 to 2 to 1. So to write the empirical formula, all I'm going to do now is I'm going to write the formula, well, I'm not going to put 1 here, but I'll put 2 here, and I'll put as O for oxygen here. But again, we're not going to actually write the little 1-to-1 ratio here. And that's all we need to do. So that tells us what the empirical formula is. So this is going to be a much, much more simplified version of what the actual formula is going to be. So we could multiply this number by 2 or by 3 or by 4, and then we might actually get what the actual compound is. But we don't have enough information to be able to do that at this stage. So what I want you to do is I want you to go through and I want you to practice this question on your own. I want you to go back and check the answers in the textbook. And if you're having some issues, first things first, remember, always convert it back to moles. And then if you are still having issues, then send me through an email or let me know in that weekly check-in. All right, so last thing that we're going to do is we're going to find the molecular formula. So to do that, we're going to be taking the empirical formula, but we also need to know the overall molar mass of that particular substance. So for example, if the empirical formula of a compound is CH2 and the molar mass is 28.054 grams per mole, find the molecular formula of this compound. So the first thing I'm going to do is I'm actually going to pretend that this is the actual compound, so that CH2 is the actual compound. So the molar mass of this pretend compound is going to be 12 plus 2 for the hydrogen, so it's going to be 14. So that would be the pretend molar mass of this simplified compound. Now you can see this here is about 28 grams. So clearly what I've done is I've doubled the ratio, or I've doubled the mass of every single thing here. So all I'm going to do is I'm just going to double the numbers here so that I have C2H4. Now let's go back. Let's just double check that the molar mass of that is going to be about 28. So remembering that carbon weighs 12 grams per mole, so that's going to be 24 for the carbon, and then I've got an additional 4 for the 4 hydrogen, so that is going to be 28. So that means the molecular formula of this particular compound is going to be C2H4. All right, so I want you to have a go at this question here. So a compound with molar mass of 128 grams is known to contain 6.3% hydrogen, 93.7% oxygen. Determine the empirical and molecular formula for this compound. So I'm going to get you to pause the video here, go away, and what I'm going to do is I'm going to pop the answer up on the screen for you. Okay, so I've just gone ahead and I've calculated the ratio here. So I've just done that the same method as what I've used before. Every single time you're given a mass, like I automatically just want you to assume in your head that you're just going to have to calculate the moles for it, because it honestly is a lot easier to work in moles than it is to work in mass. What I've done is I've determined the molar mass. I've gotten that from the periodic table, substituted that into my formula, and then I've got the value of about 6.2 moles of hydrogen, and I've got about 5.85 moles of oxygen. So I've just sort of rounded that to about 6 to 6, or a ratio of 1 to 1. So what that means is I've got a compound that has 1 hydrogen and it has 1 oxygen. Now what it wants me to do is it wants me to determine the actual formula of this. Now I'm going to pretend that this is a real compound for a second. So this would have a molar mass. Oxygen's about 16, hydrogen's about 1. So that would have a total molar mass of 17 grams per mole. So what number did I have to multiply to get to 128? Well, let's do 128 divided by 17. So I must have multiplied this by about, it's saying about 7.5. So I'm just going to say by about 8. So that means that I have a compound that has 8 hydrogens and 8 oxygens. There you go. So that is how we calculate empirical and molecular formulas using our molar mass formula. If you are having difficulties, please do give me a shout out or give me an email so that I know. All right. I'll talk to you guys again soon. Have a nice weekend. It's the last weekend before the school term, so enjoy. Bye, guys.